Hello, so let's begin one more lecture session on infinite series. Now, since past three sessions, we had been talking about various tests of convergence for positive series. And today's session, we will do one more, and that is going to be Rebase test. Also, let us remember at that moment that we have already learned the comparison test, the D'Alembert's ratio test, and Cauchy's root test. And this is the fourth one in the line. So what is that? This test says that let sigma un be a series of positive terms and limit n multiplied with un by un plus 1 minus 1 as n tends to infinity equal to L. Then this series is convergent if L is greater than 1, divergent if L is less than 1, and the test fails. That means it cannot give us any decision if L is equal to 1. So remember that in ratio test also we had to take ratio of two consecutive terms, but there it was un plus 1 to un, and here we take the ratio of un to un plus 1. So the reverse ratio of D'Alembert's ratio test is taken here, and also we subtract a 1 from that quantity and then multiply with n, and then we take the limit as n tends to infinity. And now our decision is dependent on this value of L. And this decision also, we may remember, is actually opposite to that of D'Alembert's ratio test. There the series is convergent if L is less than 1, but here it is convergent if L is greater than 1. And also the opposite in case of divergence, it is divergent if L is less than 1. And the test is inconclusive if L is equal to 1. Also note one thing, that many a times this test will be used and actually can give us a decision when the D'Alembert's ratio test fails. So let us now proceed to see some problems on the Rebase test. So the first one over here, examine the convergence of the series 1 by 2 plus 1 into 3 by 2 into 4 plus 1 into 3 into 5 by 2 into 4 into 6 and so on. So of course first we need to write down the nth member or un of this series. So what is that? We can easily observe from these terms over here that the nth term will be product of 1, 3, 5, and it goes up to 2n minus 1. And the denominator, the even factors basically 2, 4, 6, and it will go up to 2n. So if this is un, we can easily now write un plus 1 by just replacing n by n plus 1. So now here we again have these odd factors, only now it is ending with 2n plus 1, and the denominator is now ending with 2n plus 2. So now, before applying the Rebase test, let us have a look, does the ratio test works? So we just find out limit un plus 1 by un as n tends to infinity. So this un plus 1 by un, as we place these expressions of un plus 1 and un, we will see that many of the terms will vanish and we will be left with 2n plus 1 in the numerator and 2n plus 2 in the denominator. So now simplifying this, or rather taking out n both in the numerator and the denominator, we get this 2 plus 1 by n in the numerator and 2 plus 2 by n in the denominator. So as n tends to infinity, 1 by n goes to 0, 2 by n goes to 0. So finally your limit is 1. So limit is 1, that means of course the ratio test fails. So let us now see what happens if we apply Rebase test. Does it give us some value or give us some decision rather? So for Rebase test we have to use this expression now, n multiplied with un by un plus 1 minus 1. And using the expression of un plus 1 by un, what we had in the previous slide, we can now write this. This will be 2n plus 2 by 2n plus 1 minus 1. And you simplify, we get n by 2n plus 1. And this again gives us 1 by 2 plus 1 by n. So now if we take the limit of this expression as n tends to infinity, we see that as 1 by n goes to 0 under the limit, the value of the limit is half less than 1. So we have a conclusion now by the Rebase test. So the Rebase test tells us now that the series will be divergent since the limit is less than 1. Okay, so let us take one more example on Rebase test. Test the convergence of the power series. So now we have a series which contains terms containing powers of x. So x by 1 plus half multiplied with x cubed by 3 plus 1 into 3 by 2 into 4 multiplied with x5 by 5, 1 into 3 into 5 by 2 into 4 into 6 multiplied with x to the power 7 by 7, and so on. And it's also given that x is greater than 0, because we know that we can use these tests only for positive series. Okay, so let us proceed now. First, of course, we have to write down our nth term or un. Now, when we want to write un, we see that this is x by 1, x cubed by 3, x5 by 5. So it's following some pattern. But there is a problem with the coefficient. This is half 1 into 3, 2 by 4. But here the coefficient is not following the pattern. So what we do is we omit the first term and consider this one as the first. So this is second, this is third. And accordingly we write un. Now this is permissible because you will remember that we had a property that the character of convergence or divergence of a series remains unaltered if we remove any finite number of terms. Okay, so now what is un? See that if this is the third term, so this numerator will be 1 into 3 into 5 up to 2n minus 1. Denominator is going to be 2, 4, 6 up to 2n. And this one here, x to the power 7. So this is x to the power 2n plus 1 for the nth term, and denominator is also 2n plus 1. Now we write un plus 1 just by replacing n by n plus 1 over here. So we get this expression now. It's 1, 3, 5. It continues now up to 2n plus 1, and denominator goes up to 2n plus 2. And this x term over here, this is x to the power 2n plus 3 by 2n plus 3. Okay, so if we now try to find the limit un plus 1 by un as n tends to infinity, this is the expression over here. If we put these expressions for un plus 1 and un, some of the terms will cancel out. Basically the x power, we can see this is x to the power 2n plus 3 and this is x to the power 2n plus 1. So we will be left with x square, and the rest of the term will be like this: 2n plus 1 whole square divided by 2n plus 2, 2n plus 3. So again, if we take out the n square term from numerator and denominator, it gives us 2 plus 1 by n whole square divided by 2 plus 2 by n, 2 plus 3 by n multiplied with x square. So as n tends to infinity, as before, 1 by n tends to 0, 2 by n, 3 by n, they all tends to 0. So this term over here actually gives us 1. So finally the value of the limit is x square. So what does the ratio test tells us? We know very well the conclusion of the ratio test. It will tell that the series will be convergent if x square less than 1, divergent if our limit x square greater than 1. However, it cannot give us any conclusion if x square equal to 1. So this is the situation now we have to see separately, and for this case we will apply the Rebase test. So for Rebase test, again we need to write n multiplied with un by un plus 1 minus 1. And if we put these expressions for un by un plus 1 this way like this, which we have written a little bit explicitly. So this is 4n squared plus 10n plus 6 divided by 4n squared plus 4n plus 1 minus 1. And if we simplify, we have this n over here, and this gives us 6n plus 5 divided by 4n squared plus 4n plus 1. So now if we take the limit, for taking the limit, once again, we take out n squared from both the numerator and the denominator. So numerator becomes 6 plus 5 by n, and denominator becomes 4 plus 4 by n plus 1 by n squared. So as n tends to infinity, 5 by n, 4 by n, 1 by n squared, they all tend to 0. So the value of the limit is 6 by 4, or otherwise 3 by 2. And this is now greater than 1. And Rebase test tells that if your limit is greater than 1, then the series is convergent. Thus, for the case x squared equal to 1, the series is again convergent. Okay, so with these two examples on the Rebase test, we will close today's session. So thank you and goodbye. And in the next session, we will take up actually alternating series. That means series where the terms are alternatively positive and negative.